Yes, sir. There is.
So in this particular talk, I will be telling you how moon formed, how it evolved in space and time, how our understanding evolved in due course of time. This is very important for you, for the students who have joined this lecture, because that forms a basis for you to work out what should be done in future. So how this knowledge has evolved with time, this is what we will be seeing throughout this lecture. And then if I ask you regarding this, that when moon started, when was the exploration of moon started? Any one of you would answer me. It is something around the late 50s or the late 60s, early 70s that moon exploration started, but that's not exactly true. And you would be glad to know that moon's scientific study started in 1609 when Galileo Galilei pointed his telescope towards the moon. With these crude drawings, he could make out that the surface of the moon is rough and uneven, and just like the surface of the earth itself. Prior to that, it was understood that moon surface is just a perfect sphere. There are no depressions, there are no mountains. And how he found, it's very important to understand, know this. You can see in this part there is a shadow, in this part there is a sunlit area. So this type of things, the shadow is a very important indicator in remote sensing analysis. Okay, so the telescopic observations continued for a long time. Hello? Yeah, it continued for a long time. However, as I told you just now, most of our understanding about moon came from the 6 Apollo missions, which from Apollo 11 to 17, which are shown here in the color, this green colors. Okay, you can see. So these green color areas were those areas from where manned landings were carried out and samples were collected and brought out to the Earth. And then there were 3 lunar missions between 70 and 76 in this part of the moon, from where additional samples were brought robotically. So from these samples, we learned how not only moon, a planetary system should form. That type of precious samples were these, and I will come to those in a few moments. Then there were orbiters. There was a gap of about 2 decades. Moon lots is important. People felt they have learned everything about moon, but that was not the case. And I will come to the details later on. But you can see here, there were 2 missions in 90s, and that is Clementine mission and Lunar Prospector mission. These were remote sensing missions, and these remote sensing missions gave a global perspective about the moon. What is the variation in mineralogy? What is the variation in topography? All those information came from these 2 missions. So in the next few slides, you will see what we have learned from the sample return missions and Clementine mission. So here, these are the 2 sides of the moon. I'm pretty sure that none of you have seen the far side of the moon from the Earth, and the obvious reason is tidal locking, astronomical phenomena. Okay, so if you see both the sides of the moon, the near side and the far side, they are quite different. And what do you see? Huge dark areas on the moon, which are present mostly in circular area, circular sort of mountains inside. If I say mountains, it is difficult to tell you here, but yes, these are the mountains, and these are the depressions where you have this dark basaltic plains. Okay, now this type of areas are dark because they are made up of this type of rocks, which have abundant FeMg rich minerals. I will not use any technical jargons, so you try to remember it is FeMg rich minerals due to which these are dark areas. Then these type of areas are light because it is made up of calcium, aluminum rich minerals. Okay, so that is why which is known as anorthosite, but you should remember it is calcium, aluminum rich mineral. Then if you see here, it's a very nice feature with lot of rays here. Actually, this is a crater called Tycho crater on Moon. Okay, and you can see the lot of rays. So why do we see rays on Moon? Because this is also same composition. This is also same composition. However, their maturities means these areas are old. These areas are young. So any young area will be having higher albedo than the older area. So this is how Moon surface gets its soil. Okay, due to the impact of solar wind and due to the impact of micrometeorites, it becomes dark with age. Okay, so one of the impact of the object which came out during the impact which produced Tycho crater was found very at large distance, and it has caused a landslide. Just imagine how much mixing would have happened. This is just around 85-kilometer diameter crater, and it has thrown material up to this distance. So these are very large ones. So these are basically called basins. I mean, any crater which is having diameter greater than 300 kilometers are called basins. Okay, and these are craters. The smaller ones are called craters. Fine. Now let us see this far side. Now, why it looks too different? It's a very big question in lunar science. There are certain hypotheses which explains. One hypothesis says that this is thick. This part of the Moon, the crust is thicker, due to which the magma which came up from interior could not come out. That is why it is, you don't see them here. But that is also debated, and it is still a big problem. Now, if you see here, there is a very low, there is quite a low albedo area here. What is this? This is South Pole Attican Basin on the Moon. Okay, this is the largest impact basin on the Moon, which is having a diameter of 2,500 kilometers and a depth of greater than 8 kilometers. This is one of the oldest basins on the Moon, which is about 4.25 billion years old or more. The Moon should have broken by this impact, but it did not. Why is it so? This is another question in lunar science. Let's see these craters at a in a zoomed-in view. See, the craters range in size from micron size. This is a micron size crater, and as the size increases, this is a simple crater, simple bowl-shaped crater with a flat floor. Then you can see we see a central peak coming up. The crater walls are also terraced. So this is a complex crater. This transition on Moon occurs at a diameter of about 15 kilometers. So you have to remember these things, and this varies. On Earth, it will be lesser than that because it is dependent on gravity of the planetary body. So as the size increases and we move on to the basin related things, it is 320 kilometer in diameter. You can see this peak, central peak has been converted into a peak ring. And then at around 1,000 kilometers, you see multiple rings in this basin. So as a function of size, the morphology systematically changes. Okay. Now, this was this was the first study from our country where we have used this central peak data. We found the composition of the data, and for the first time, we told what is there in this subsurface, because these central peak, they tell us what is present in the subsurface, maximum depth. If you study a 100-kilometer crater, it is a 10-kilometer depth which you are sampling. And then we found that, number of plutons or mantle rocks we could find out on the Moon. And the take-home message from this slide is that craters serve as windows to the interior of the moon. So from remote sensing, we can just study the surface. But if we know the morphology and we study the walls, the central peak, then we can tell what is there in the subsurface also. Well, coming on to the major volcanic features on the moon, then as I told you, there are vast basaltic plains. Then we have pyroclastic deposits, which is outcome of explosive activity on the moon. This is silent volcanism, this is explosive volcanism. And then you can see here the cobra head. These are the lava tubes. Okay, here from this part, this magma has come and the lava flew in this. This is the largest, you can say, sinus relay on the moon, and this is known as Valles Cotteri. Then there are few silicic domes on moon. Okay, when the viscosity is high, the viscosity of the magma is high, it cannot flow to larger distance, just accumulates like this and produces a dome-like structure. So these are the major volcanic features on the moon. Now, if we put age, because unless we talk about age, we cannot, really quantify things, how things have evolved. So this here, the cratering history of the moon is shown. So you can see during the early time, the moon was impact. The rate of impact was very high. Then it dipped around this 4.4 giga-annum. It dipped. Again, around 3.9 giga-annum, there was a peak. Now, this is a period is called lunar cataclysm or late heavy bombardment. Then, after that, the intensity has fallen down, and still it is like this. So, this is how the impacts have happened on moon. Just imagine about Earth. Similar situation was there on Earth. So many impact happening, and around 3.9 giga-annum. What would happen situation on the Earth? This is a very intriguing question. Then volcanic history of the moon. When those dark plains were formed on moon, a lot of them were formed during the early phase when moon was having a lot of internal energy. At that time, this 3.9 giga-annum, greater than 3.9 giga-annum, lot of volcanism happened. Then the main phase volcanism was between 3.8 to 3.1 giga-annum, and up to 1.2 giga-annum, it was the late phase. This was our understanding of the volcanic history of the moon when before our Chandrayaan and missions flew. Well, now see, Jolliffe et al. In 2011 used all sorts of data sets, compositional, morphological, remote sensing, sample, everything, and he classified moon into different type of crustal terrains, different type of areas, you can just say. Okay, for example, this area, just take it, this is known as Procellarum Greek terrain. Don't go into this technical term, just remember it is enriched in heat-producing elements, radioactive elements, that's all. Okay, then if you see this area, the South Pole Attican terrain. So this type of terrains were felspathic highland terrain. So this type of terrains were formed by Jolliffe et al. Well, so here I have summarized the origin and evolution of moon theories on the basis of all those observations I just mentioned. So moon formed due to giant impact hypothesis. Okay, a Mars-sized object called Theia impacted the proto-Earth. Then what happened? A disk of debris was formed, and this disk coalesced to form moon. What happened afterwards? Afterwards, there was a lot of heat inside the system because of accretion. It is due to accretion, moon has formed, right? So there was a lot of heat. This heat has molten the moon, okay? And a lunar magma ocean was formed. So what happened in the lunar magma ocean? Crystals, when it started cooling, crystals start forming. And the those crystals which were having light, means enriched in calcium and aluminum, they floated on the top, forming this crust. And those crystals which were having higher iron magnesium rich minerals, they are seen in this part. So they settled in this part, forming the mantle of the moon. Okay, so giant impact hypothesis followed by global magma ocean hypothesis. These two explains, one explains how moon formed, the other explains how the crust of the moon formed, how the differentiation of moon happened, crust, mantle, core of the moon formed. Okay, then suppose your moon has formed around 4.4 giga-annum. What happened? Mare volcanism happened. Then formation of basins, as I told you. And I will just show you a movie which will give you a better feeling right now. Are you getting the voice? Apartment. Main phase of Mare volcanism. Okay, so while they told us many things about moon, several new questions also arose, and some of them are listed here. Do we have water on the moon, or it is bone dry? Lunar prospector gave indication of presence of hydrogen-bearing compound, but whether it was H2O, they could not confirm. Samples were found to be bone dry. Then is the available samples in the repository sufficient to cater to the geological diversity of the moon? Means whatever sample we have from those missions, is it sufficient or we need new samples? Then what is the geological state of the moon? Is it geologically dead after 1 giga-annum? So these are some of the compelling questions which actually led to a new era of lunar exploration, which started this smart one, and you can see our Chandrayaan missions here. Okay, Chandrayaan 1 in 2008, 2 in 2019, 3 in 2023. So number of missions have gone to moon to answer these questions, and these are only few which I've listed. Okay, there were several questions. Before I go to some of the results, selected results from this, since they are students, they would be delighted to know that we now have a crater on the moon. This is a simple crater on the moon. This part, in this part of the moon, which is named after Dr. Vikram Ambalal Sarabhai, the father of Indian space program. Okay. And This is an incredible view of the moon from OHRC on board Chandrayaan-2. This is the best resolution data available from any mission. You can see boulders, small craters in the area, and these data have played a key role when we landed on the moon during Chandrayaan-3. Okay, now coming to the findings from Chandrayaan mission, you can see here for the first time on the basis of this particular depression in the reflectance data, okay, around 2.8 micron, it was found that moon surface is having hydration. There is a surface hydration of moon surface, and you can see in the polar areas, the hydration was found to be more. Hello? Okay, then these deposits, I'm in a meeting, please. So then you can see here, these deposits of ice mixed with regolith are present in the permanently shadowed regions of the moon. At poles, these regions have not seen sun for 2 giga-annum. Okay, so these areas have not seen sun, very cold, about 70 Kelvin is the temperature there. So any water molecule which has come to this area should stay there. Okay, thus it can be inferred that the moon is not bone dry. Now coming to the new rock types on the moon, as I told you, yes, there were lots of rocks which have not been sampled during Apollo and Luna missions. And one example is this MG spinel anorthosite. This is a gemstone MG spinel, MgAl2O4. And this is found normally at depth in Earth. But on moon, there are surface exposures of this. And this rock, this mineral, in combination with this particular rock, has never been reported from in more than 380 kgs of lunar samples. So this was a really surprised finding from the Chandrayaan-1 data, MQ data. Then there were potential exposures of mantle rocks around these big basins of the moon. And one example is shown here. So these are the mantle rocks. Earlier it was thought even these big basins cannot bring out the mantle rocks of the moon onto the surface, the rocks from the very deep interior of the moon. But this thought process has changed now. Now people expect the mantle rocks on the surface. And here, these are the rocks on the moon which are yet to be sampled. Okay, only 2 examples I'm showing you. There are many more. Then coming to the recent volcanism of the moon, at this near side, far side boundary on the western limb of the moon lies the Oriental Basin, which is the prototype multi-ring basin on the moon. And this in the northwestern part of this basin lies a tiny crater which is known as Lowell crater. And Lowell crater is hosting one of the very exciting area on the moon. And this area actually, you can see here this type of things. If you go to Hawaii, you will see this type of dark flows and structures. Okay, but on moon, the first and foremost thing which comes to anybody's mind is that this crater forms, lot of melt will form here, impact melts, and this will just flow and make this area unit. But our detailed study showed that it is not as simple as this. These are actually volcanic eruptions on the moon, which would have happened merely 2 to 10 million years ago. And this indicated, you just see this zoomed in views using LROC NAC camera data, and you can see superposed flows, pit surrounded by vesicles, then pit showing extrusion of melt. I mean, so many evidences were there, even spectral evidences, composition-wise also we could actually see that this composition is different from the target rock, which actually proved our point. So the moon had volcanism around 2 to 10 million years ago, and thus the moon is geologically active. This is what we propose. Now, here we further, you can see this is another incredible view of the flows in the same area. You can see these are superposed flows of different generation, and here faults and fractures have formed. So we have recent volcanism, we have recent tectonism. These flows are confined by a topographic barrier. So this source has to be here, okay, which is shown as Z, crater Z here. It's tiny crater, okay. We further, studied this area, the whole Lowell crater, and found that it is a very important crater on a moon, which can address to several important questions of the lunar geology, like its nature of the mantle of the moon. Mantle rocks could be present here, and several other which I already discussed. Now the question was, what is fueling this recent volcanism on the moon? And to answer this, we have to move in different areas. So what we did earlier, people, whatever 1.2 gigaannum volcanism I talked to you, they were found mostly in this area. So people have proposed those heat producing elements which I mentioned earlier were responsible for the volcanism on the recent volcanism on the moon. But what we did, we took this particular area. Here we found lava crater, and here there was already report. So we selected this area, and we were delighted to find nearly 700 million year volcanism in this Grimaldi basin, and tectonism as early as 50 million years. The moon is geologically active indeed. But, well, if you move to this area actually we started a new type of study on moon. These basins are so old, they are so degraded, they're not seen. Only a little bit of depression in this area, but there are some basaltic areas which we can see here, small craters, small lakes of dark areas. Okay, so for the first time, we studied geology of an obscured ancient impact basin on the moon, and we also found recent volcanism in this area up to the late phase volcanism, 1.5 gigaannum. Okay, so then we move to this Australian North, and this Australian North, this is a very unique basin here in this part, just in the western limb of the moon, eastern limb of the moon. This is the eastern limb of the moon, and here this basin, for the first time, it was reported by Grail. There is absolutely no evidence of this impact basin in the area. This is lost, completely lost. So Neha, actually, who is the moderator of this study, of this presentation, she carried out a detailed analysis based upon the understanding of impact basin and found late phase volcanism occurred in this basin also. And I will just tell you that this is this Scaliger crater, and this is the Lacus solitudinus. She found this recent volcanism in Lacus solitudinus. Okay, and this is a big pluton. Pluton is a technical term, a big subsurface magma body. Okay, that is Pluton. It could be the largest massive Pluton on the moon, okay, which is shown by Scaliger crater. Okay, and this basin could be even older than South Pole Attican basin. Just simple thing, don't get into the complexities here. This was the heat producing areas, and if this is only responsible for the young volcanism, then why we are getting in so many areas? This is a big question. This means something else is fueling volcanism on moon, recent volcanism on moon. That is what we have to understand in future. So we wrote a new volcanic history of the moon, the topical phase. This was what we added, and then we brought down the late phase to 700 million years. These are my concluding remarks. The missions to the moon during the past decade and a half have considerably changed our understanding. Geologically, the moon is much more diverse, and contrary to the expectations, the moon shows evidences of recent volcanism and tectonism, and it is enriched in volatiles. These findings are not in agreement with our earlier understanding of the origin and evolution of the moon. So our understanding is changing. To address them, new samples are required, and in situ missions are required to address these issues and put forward another giant leap in the field of lunar and planetary exploration. So we have already selected few potential landing sites on the moon for in situ and sample return missions. There are several, but these are the few ones, and each of them are very important. Okay, if we see here Lunar Gamma, this will tell you about the magnetic anomalies of moon. Grimaldi Basin, recent volcanism, tectonism, as I told you. Then Compton-Belkovich, silicic volcanism, endogenous water. Endogenous means from the interior of the moon, not from the outer sources. Then South Pole Aitken Basin. This is, I told you, okay. Okay, so and you can, why you should miss this Shiv Shakti point in the South Polar Highland region. If we study this, we can tell about what is the composition, what is the nature of the South Polar Highland region. Is it different from other areas? So multiple missions with varying capabilities are required to address these questions. And also you should think from now onwards, where do we want our Indian base station in the future? And that is why I just put this slide to show you everybody is moving towards the poles. Do we also need to move toward poles for Indian base station? Because pole has water ice. This is the known thing. In the equatorial belt also, we have lots of advantages. For example, we have natural habitats, lava tubes, abundant key natural resources are there. We have to think, you have to think, not me now, it is you, because you will be witnessing this thing in future, and the journey has just begun. Long way to go.
जी हाँ, आप अपनी स्क्रीन पे देख सकते हैं कि हम लैंडर मॉड्यूल.
People are applauding. Let us all wait to hear from the Secretary, Department of Space and Chairman ISRO, Shri S. Somnath.
लैंडर मॉड्यूल पूरी तरह से सेफली और सॉफ्टली चंद्रमा के सतह पे लैंड हो चुका है. ये हम लोगों के लिए बहुत ही गर्व की बात है. हिंदी में एक कहावत है कि चंदा मामा दूर के, लेकिन अब हम ये कह सकते हैं कि चंदा मामा अपने घर के.
बहुत ही उम्दा.
So if Chanda Mama is apne ghar ke, then it means Chanda Mama is for mankind. So I would like to end my presentation with a statement: let's explore the moon, not exploit it. Thank you so much.